Welcome to the deep dive. Today we're diving into the James Webb Space Telescope.
Oh, yeah.
You've probably seen those crazy pictures from it, right?
Yeah, those colorful images.
Yeah. But have you ever thought about what actually makes those pictures so clear?
Most people don't.
It's the telescope's mirror.
Yeah.
And it's not just like a big piece of glass or something.
It's so much more complex.
Yeah.
Yeah, it's actually made up of 18 separate segments.
Oh, wait.
All hexagonal.
18
Yeah.
hexagonal.
And they all work together perfectly.
To act as one giant mirror.
Yeah, like a 21-foot mirror.
So it's like some giant puzzle in space.
Well, they did assemble it on Earth, but the real challenge
Okay.
was aligning those segments in space.
Yeah, I can't even imagine trying to align 18 mirrors perfectly.
Millions of miles away in the vacuum of space.
Yeah, in space.
Yeah.
Incredible.
How do you even do that?
So they use a technique called wavefront sensing.
Okay.
Think about shining a flashlight on a bumpy surface.
Okay. The light's going to scatter everywhere, right?
Mm-hmm.
That's what they're fixing with the mirror.
Ah,
They're analyzing how the light bounces off the mirror
okay.
and then using that information to smooth out those bumps.
So they're basically like taking blurry images and then using those to fine-tune the mirror?
Exactly. It's like a continuous process.
Oh, wow.
They take these blurry pictures,
Okay.
analyze them, and then send commands back to the telescope
Gotcha.
to adjust everything.
So it's like a never-ending job.
Pretty much.
I mean, space is a pretty harsh environment.
Absolutely.
Wouldn't things like temperature changes affect it?
You're right. The telescope has to deal with crazy temperature swings.
Yeah.
And even tiny vibrations can throw off the alignment.
Oh, really?
They call these vibrations tilt events.
Tilt events? What's that?
Imagine a tiny little earthquake on the telescope.
Oh, so like the mirror is constantly getting these little earthquakes.
Yeah, that's a great way to put it.
And they just have to keep adjusting.
Yeah. And what's really amazing is that even with all those challenges,
Oh, wow.
the telescope is doing way better than they thought it would.
Really? How much better?
It's performing 6 times better than they planned.
6 times.
6 times better.
That's insane.
Yeah, it's incredible.
So what does that actually mean for the images?
It means we're seeing things we never thought possible.
Like what?
Sharper images.
Okay.
We can see fainter objects
Wow.
and a much clearer view of the early universe.
Okay. You definitely have my attention now.
Good.
So we're not just talking about pretty pictures here.
Oh, no, not at all.
We're talking about groundbreaking discoveries.
Absolutely. Because of this precision,
Okay.
we're seeing galaxies from the universe's infancy.
So we're literally seeing back in time.
We are seeing back in time.
Wow, that's mind-blowing.
It is. And it's not just about looking back.
Okay.
This level of precision
Yeah.
opens up so many possibilities for the future of space telescopes.
Okay, what kind of possibility?
Well, one project that's really cool.
This is the Habitable Worlds Observatory.
Okay.
This telescope will be specifically designed to search for signs of life.
Wait, searching for signs of life.
Yeah, on other planets.
That sounds like science fiction.
It does, but thanks to Webb, this kind of mission is becoming more realistic.
So how would they even do that?
So we can look for things like chemical fingerprints of life
Okay.
in the atmospheres of planets.
So you can analyze the atmosphere of a planet that's light years away.
It's based on a pretty simple principle.
Okay.
When light passes through an atmosphere, certain wavelengths are absorbed by the gases.
Oh, so they're like playing detective with starlight.
Exactly. We're searching for those subtle signs of life.
That's incredible. And it all comes back to that mirror
It really does.
and the team that keeps it working.
It's a testament to just human ingenuity and that desire to explore.
I'm hooked. What else can you tell me about this telescope?
Oh, there's so much more to explore.
Okay.
Let's dive into how they actually adjust those 18 mirror segments. Yeah, how do they actually do it?
And how those tilt events affect everything.
Okay, I'm ready.
Join us for part 2,
Let's go.
where we'll unpack all of that.
Perfect.
Welcome back.
I'm still thinking about that last part.
It's fascinating stuff.
Yeah, to think we could find life on other planets.
Yeah, it really is a remarkable time.
Okay, so last time we were talking about tilt events
Yeah.
and how they can mess up the mirror.
Right.
Can you tell me more about what actually happens during one of those?
Okay, so imagine this giant structure in space, right? Exposed to crazy temperatures and the vacuum of space.
Yeah.
Over time, stress builds up in the materials.
Okay, that makes sense, but what does that have to do with tilt events?
Well, eventually that stress has to go somewhere.
Right.
It's like bending a stick until it snaps.
Oh, okay.
In the case of the mirror, it's not an actual snap,
Oh.
but a tiny sudden release of energy.
So like a microscopic earthquake
Exactly.
rippling through the mirror.
And even those tiny tremors can be enough to shift the mirror segments.
Really? Even those little tremors?
Oh, yeah. They're talking nanometers.
Nanometers, that's like unbelievable small.
It's a constant battle for the engineers.
I bet.
They have to account for everything.
Yeah.
Temperatures, vibrations, even sunlight.
Wow.
Just to keep that mirror working.
So how do they actually adjust it?
Well, each mirror segment has these tiny motors attached to it.
What, little tiny wrenches or something?
No. They're called actuators.
Actuators. Okay, what are those?
Think of them as like micro adjusters.
Oh, okay.
6 of them control the position of the mirror.
Okay.
It's up, down, left, right.
So each segment can move in all those directions.
Exactly. And then there's a 7th actuator.
Oh, wow.
That can actually change the curvature of the segment.
Wait, they can reshape the mirror?
While it's in space.
While it's in space.
Yeah, it's pretty wild.
That's crazy.
Yeah, and it's all thanks to these actuators.
So how do they know which ones to adjust?
Well, remember that wavefront sensing we talked about?
Oh, yeah, the blurry images.
Exactly. They use those images to create a map of the mirror's surface.
Okay.
And that tells them where the alignment is off.
And then they use that map to guide the actuators.
They have these algorithms.
Oh, wow.
That calculate exactly how much each actuator needs to move.
That's incredible.
It's like a giant puzzle.
Yeah.
But instead of pieces, they're adjusting these motors.
So how often do they have to do all this?
It depends. Sometimes the mirror can be stable for months.
Oh, wow.
But then something like a tilt event might happen.
Yeah.
Or the telescope might move a little.
And then they have to adjust it.
Exactly. It's all about responding to the telescope.
Wow. So it's never really done?
Pretty much. It's constantly being monitored.
It's amazing to think that all this is happening millions of miles away.
It's really a testament to what we can achieve.
Yeah.
With engineering and technology.
Okay, so we've talked about how they adjust it.
Yeah.
But could these tilt events damage the mirror?
That's a good question.
Yeah.
The engineers are always watching for that.
Okay.
So far, the mirror seems to be holding up really well.
So no need to panic yet?
No, not at all.
Okay, good.
It was designed to handle this stuff.
But they're still keeping an eye on it.
Of course, we want it to last as long as possible.
Makes sense.
It's all about finding that balance.
Yeah, pushing the limits but keeping it safe.
Exactly.
Okay, so we've talked a lot about the engineering.
Yeah.
Who are the people behind all this?
Oh, it's a great team.
Yeah.
You've got optical engineers.
Okay.
Software developer.
So it's not just one person at a computer.
No, it takes hundreds of people.
Wow.
All working together.
It sounds like a well-oiled machine.
It really is.
Like a symphony of science.
Yeah, that's a good way to put it.
Okay, so we've covered the how.
Mm-hmm.
Now I want to know about the what.
Okay.
What's Webb actually seeing?
Well, get ready to be amazed.
Okay, I'm ready.
Because Webb is rewriting the textbooks.
Okay.
It's seeing everything.
Like what?
From the earliest galaxies to the atmospheres of exoplanets.
Wait, so we can see the very first galaxies?
You can see back to the universe's infancy.
And we can see the air on other planets.
They can analyze their atmospheres.
This is incredible. I can't wait to hear more.
Well, that's the story for part 3.
Okay, let's go.
We'll dive into all the amazing discoveries.
Welcome back to the deep dive. We've talked about how incredible Webb's mirror is.
It's a game changer.
Yeah, but now I want to hear about the discoveries.
Okay, you ready for this?
I'm ready.
Webb is seeing the very first galaxies.
Whoa, hold on.
Yeah, just a few 100 million years after the Big Bang.
So we're talking about when the universe was like a baby?
Exactly. We're seeing the universe in its infancy.
What are those galaxies even like?
They're completely different from what we see today.
Oh, really?
Yeah, they're smaller.
Okay.
Less structured. Just these bright clumps of stars forming and evolving super fast.
So it's like a completely different universe back then.
It really is, and that's what's so fascinating.
Yeah.
We're seeing how galaxies have evolved over billions of years.
It's like watching a cosmic time lapse.
I love that analogy.
Yeah.
And it's not just galaxies.
Oh, right. You mentioned star formation.
Yeah, Webb is also giving us incredible views of how stars are born.
I mean, we can't even see stars being born with our own eyes, right?
Right. They're hidden in these giant clouds of gas and dust.
Yeah.
But Webb can see through those clouds.
What?
Yeah, it's got infrared vision.
Oh, wow.
So it's like it has special goggles.
So we can see stars being born?
Exactly. We're seeing proto-stars collapsing and igniting.
It's like watching the spark of creation.
That's a beautiful way to put it.
And we can see this happening all over the galaxy.
We can, and it's helping us understand how our own solar system formed.
That's amazing. Okay, so we've got ancient galaxies, star nurseries.
Yep.
Now, what about exoplanets?
Ah, yes.
Is Webb looking at their atmosphere?
It's doing it right now.
Wow.
And in incredible detail.
So we can really see what the air is like on other planets?
We can see what molecules are present.
So what have we found so far?
Well, we're finding things like water, and carbon dioxide.
Okay, yeah, those sound familiar.
But we're also finding complex organic molecules.
Wait, organic molecules? Those are the building blocks of life.
Exactly. And that's why this is so exciting.
So are we close to finding life?
It's still too early to say for sure.
Okay.
But Webb is helping us narrow down the search.
Yeah.
We're finding planets that could potentially be habitable.
Planets with liquid water.
That's the key ingredient.
It's like we're on a cosmic treasure hunt.
The biggest treasure hunt of all.
Trying to answer the question, are we alone?
And Webb is giving us the tools to do it.
This is unbelievable. I'm so glad we did this deep dive.
You too.
It's been mind-blowing.
It's just the beginning.
It really makes you appreciate how much is out there.
It does.
And how much we're still learning.
It's an incredible time for astronomy.
So the next time we see one of those amazing pictures from Webb, we'll know there's so much more to it.
There's a whole universe of stories behind each image.
Well said. Thanks for joining us on the deep dive.
My pleasure.
Keep looking up, everyone, and never stop exploring.